Yes, whatever you are going to learn this year, again, some of the reactions may be repeated next year also in some of the chapters. So that's why here you just try to analyze the reaction, or you try to understand the logics behind the reactions. And then once you are thorough with the second year chapters, what I feel is this chapter becomes easier for you. But what we are going to start now with the basics of this hydrocarbons. So shall we start, students? Are you ready, all of you?
Yes, sir.
Yes. Yes. Let us start with hydrocarbons. So I hope you know what are hydrocarbons. The name itself is self-explanatory over here. So hydro means hydrogen, carbon means carbon. So the compounds which contain carbon and hydrogen only, no other elements, only these two elements. One is carbon and another is hydrogen. The compounds contain only these two elements are called as hydrocarbons. So these hydrocarbons, why we need to study these hydrocarbons? So we need to study these hydrocarbons. These have lot of applications in our daily life. So you can just see some important applications I am just giving you here. One of the application you can see we use as fuels. Why we can use these hydrocarbons as fuels? So hydrocarbons can be used as fuels because when we burn hydrocarbons, they are going to liberate a lot of energy, exothermic reactions. So a lot of energy is liberated. Delta H is negative for such combustion reactions, and lot of energy is liberated, and that energy can be easily used to convert into mechanical energy. So that's why we can have certain common basic things to be understood for about these hydrocarbons. So LPG, CNG, compressed natural gas, LNG, liquefied natural gas, all these are the fuels what we are using nowadays in day-to-day life. And apart from this, we also have applications of this in the preparation of some important polymers which we use in day-to-day life. So we all of you heard about the polyvinyl chlorides, polypropylene, polystyrene, all these we are using in our day-to-day life as plastics. And in the preparation of these polymers, these hydrocarbons play important role. And also we use hydrocarbons in many ways in the preparation or manufacture of dyes and drugs also. So it has a lot of applications, and because of that, we should have at least little knowledge about these hydrocarbons in this. So how we classify hydrocarbons? Main classification of hydrocarbons, based on what we classify these hydrocarbons. So based on the structure of hydrocarbons, we can classify it into different classes. Say hydrocarbons. Can anybody tell me what is the classification we can do here based on its structure? Quickly, anyone? No reply. Anyone?
Please interact, students.
Yes. So hydrocarbons based on structure, you know, one of the important feature of carbon is it can form chain-like structures, it can form ring-like structures. So therefore, we can say hydrocarbons can further be classified into as open chain hydrocarbons and closed chain hydrocarbons. So that means open chain means you will have the carbon atoms attached together in the chain form like this. Closed chain means in a ring-like structure it can form something like this. So we can say carbon can have different types of attachments with each other in the form of open chain or in the form of closed chain. So this is the basic fundamental classification, broad classification of hydrocarbons, open chain hydrocarbons and closed chain hydrocarbons. Further, we can classify open chain hydrocarbons as saturated and unsaturated hydrocarbons. So what do you mean by saturated and what do you mean by unsaturated? I hope all of you know what is meant by unsaturated and what do you mean by saturated. Can anyone tell me? Saturated, the meaning is very simple. If we have carbon linkage and carbon has only single bonds, no double or triple bonds. Carbon has all single bonds and carbon is sp3 hybridized over here. So such type of linkage between the carbon atoms, no double or triple bond, all carbon atoms have single bond such. That means the valency of carbon is 4 and the 4 valency is completely satisfied over here. So all 4 different bonds the carbon is making. So therefore its bonds when means all 4 electrons, we write in dotted structure like this. So all these 4 valence electrons of carbon are involved in bonding with some different atom or group. So sharing these 4 electrons with different atoms or group and forming a different, all 4 different bonds. So such type of open chain compounds are known as saturated open chain hydrocarbons. Unsaturated in the sense carbon is not having all 4 different bonds, means at least one double or triple bond may be present between the carbon atoms like this. Say if carbon atom has double bond with itself like this, it is an unsaturated compound. Valency is 4 means carbon can form only maximum 4 bonds. So that means you can have remaining 2 bonds for this carbon because already it has made 2 bonds here, remaining 2 bonds for this carbon. So this is the basic structure of an unsaturated hydrocarbon, open chain hydrocarbon. This is the basic structure. So here at least one such double bond is present in the chain, then the compound is known as unsaturated open chain hydrocarbon. And if we have carbon-carbon triple bond like this, now can you tell me each carbon can have maximum one more how many bonds? Remaining one bond only for this. Because 3 bonds already made between the carbon atoms, it can make one more bond. So maximum 4 bonds it can make. That's all. So these two are unsaturated hydrocarbons because all 4 bonds are not different here. So at least one is triple or double bond. Such bonds or such classification we call it as unsaturated open chain hydrocarbons. So closed chain hydrocarbons you can see alicyclic or aromatic hydrocarbon. See, we also have open chain or closed chain. We can call them as aliphatic and aromatic. One more broad classification we can do in the first chapter you must have come across. Aliphatic and aromatic. So aliphatic open chain, we can say, see this saturated and unsaturated compounds can also be called as aliphatic open chain hydrocarbons. Alicyclic means the compounds are cyclic in nature but aliphatic. So they are aliphatic in nature. So they are not aromatic. So if you want to say a compound as aromatic, there are some criterias. So I'm going to discuss about the criterias for a compound to say it as aromatic in the later part of this chapter. So right now, aliphatic means they have some different characteristic properties. Aromatic means they will have, such compounds will have some different characteristic properties. So there is a difference in their chemical properties, aliphatic and aromatic. But aliphatic cyclic compounds may have similar characteristics of open chain aliphatic compounds. So we can further classify these aliphatic compounds as again saturated and unsaturated. Further, we can classify like that how we have classified open chain compounds as saturated and unsaturated. So saturated, unsaturated, all of you know. Further, we can classify as alkanes, alkenes, and alkynes. This is in case of open chain compounds. And further, we can classify alicyclic as saturated and unsaturated, and cycloalkanes, cycloalkenes, and cycloalkynes. Meaning, here alkanes means open chain compounds like this. All are single bonds between the carbon atoms. Alkenes means at least one double bond will be there. Alkynes means one triple bond will be there in the chain. Whereas cycloalkanes means the carbons are bonded in cyclic manner. Say if I take C like this, C in this case like this. If I write all carbon-carbon single bonds and carbon has maximum 4 bonds, here you will find already this carbon is bonded with 2 other carbon atoms, means remaining 2 bonds it can have, with hydrogen, and remaining all are having 2 bonds with this. So this is cycloalkane because there is no, all carbon atoms are differently bonded with different atoms or groups. Therefore, it is cyclic compound, but having an aliphatic character here. And it also has all 4 different bonds. Therefore, we can call cycloalkanes. Similarly, cycloalkene means, let me write an example like this. We can see I have closed chain compound having 5 carbon atoms over here. And what I'll do is, between say one of the carbon atoms, I'll write double bond. So like this, if I write. So for this, these 2 carbon atoms already 1, 2, 3 bonds are there, remaining 1 bond they can have. And other carbon atoms can have 2 more bonds like this. So this at least 1 double bond in the ring, if we have, we call it as cycloalkenes. Similarly, at least 1 triple bond in the ring, if we have, then we can call it as cycloalkynes. Like this. If I have triple bond, there are no hydrogens for this. Remaining you can have like this, because already 4 bonds are satisfied for both of these carbon atoms. Let me write 1 and 2. For these 2 carbon atoms, all the bonds are satisfied. 4 bonds are over, because organic chemistry, you must keep in mind that carbon has 4 bonds, not more than that. If it is a neutral compound, then it will have 4 bonds. Otherwise, it won't be neutral. Either it will be having positive charge, carbon will be having positive charge, or negative charge. So this is the broad classification of these hydrocarbons. And aromatic compounds can further be classified here as benzenoid and non-benzenoid aromatic hydrocarbons. Benzenoid, non-benzenoid aromatic hydrocarbons. So what do you mean by this benzenoid and non-benzenoid? Means if the aromatic hydrocarbon contains benzene ring, at least 1 benzene ring, then we call it as benzenoid aromatic hydrocarbons. Non-benzenoid aromatic hydrocarbons means the aromatic hydrocarbon which does not contain any benzene, but still it is having aromatic character. So when I deal with aromatic hydrocarbons as a separate part in this chapter, I'm going to go in detail with examples about this benzenoid as well as non-benzenoid aromatic hydrocarbons. Any doubt you have in this classification, anyone? Any kind of doubt? Okay, then let us move ahead with we are going to discuss in this chapter mainly about alkanes, that is open chain, aliphatic, open chain, saturated hydrocarbon, and alkenes, aliphatic, open chain, unsaturated hydrocarbon, and alkynes. So plus aromatic hydrocarbons. So now let us take alkanes first. We just go little in detail about alkanes. What are alkanes? So alkanes are saturated hydrocarbons. So under normal conditions, they are not reactive at all. So they are not much reactive. Paraffins. So you can just observe the term over here, paraffins. Param affins. So param means little, affins means affinity. So they have very little affinity for any kind of reagents, like say acids, maybe bases, maybe oxidizing agents, maybe reducing agents. They are not having any kind of reactivity with these reagents. Therefore, under normal conditions, hence we call them as paraffins. And these are saturated open chain hydrocarbons containing only carbon-carbon single bond adjacent to each other. Already I explained this. And examples you can take methane, ethane, etc. So one of the first member of this group, that means general formula for alkanes is CnH2n plus 2. What is N here is number of carbon atoms. So the first member of this alkanes becomes methane because meth means only one carbon atom. So CH4, this is the formula for methane. So methane is the first member of alkane and it is generally found in coal mines or marshy places where we find greenery and wet area. So in such places, we are going to find this methane gas. So coal mines or marshy place, we get methane gas. And general formula, CnH2n plus 2, where n can take the values 1.1. N is number of carbon atoms you can consider here. Next is this general formula, n is equal to 1. You can see C1 means methane is the first, and it is a marsh gas, or another name for this is fire damp. So n is equal to 2. You can see C2H6, which is the second member of the alkanes family, and alkanes becomes the homologous series. You must have come across this term homologous series. So homologous series is nothing but series of organic compounds which successive members differ by CH2 group or the atomic mass of 14U. So they differ. Say, for example, if I take methane as an example first, this is the next member of this will be C2H6 like this. And the difference between this is first member of the family, this is second member of the family. What is the difference between these two is CH2. So this, if you add CH2, remove one hydrogen and add this CH2, so you will get this particular C2H6 as the second member of the family. So CH2, what is the atomic mass of carbon? 12, and hydrogen is 1, 1 plus 1, 2. So total mass you are adding is 14. That's why I told 14U. So the successive members differ by CH2 or 14U with respect to their mass. We call them as alkanes, or the homologous series called alkanes. So generally the characteristics of homologous series, they have general formula. They can be represented by some general formula. Here general formula is CnH2n plus 2. So they will have similar chemical properties. So they have regular gradation in their physical properties. All these are different characteristics of homologous series you already have come across. Now let us discuss about structure of alkanes. As I already told you, in alkanes, all carbon atoms are sp3 hybridized. So sp3 hybridized means hybridization of carbon atom. Sp3 means they have tetrahedral geometry. So sp3, how many sp3 hybridized orbital will be there? 1, 2, 3, and 4. Or sp3 hybridized orbital will have same shape and same energy. You must have come across hybridization concept in chemical bonding chapter. So there you have learned about hybridization. So one s orbital of carbon and 3 p orbital of carbon mix with each other and form 4 sp3 hybridized orbitals. All s orbital has different shape and energy. P orbital has different shape and energy compared to s. So after mixing all these orbitals, you will get the hybridized orbitals having same shape and same energy. So here 4 sp3 hybridized orbital. Each sp3 hybridized orbital will have one unpaired electron, and these sp3 hybridized orbital overlap with s orbital of hydrogen. So hydrogen 1s1. So 1s orbital of hydrogen, 1s orbital of hydrogen, like this they will overlap. So hydrogen shares its electron, each hydrogen shares its electron with this sp3 hybridized orbital. So here overlapping is taking place between s orbital of hydrogen and sp3 orbital of carbon, forming CH bond. So that is one of the important point to be understood here. So C bond length, if you have, say, next member C2H6 like this, now both carbon atoms are sp3 hybridized. This is sp3 hybridized. This is also sp3 hybridized. So both are sp3 hybridized. But what is the bond length between carbon and carbon here is 154 picometers or 1.54 angstrom units. And what is the bond length between carbon and hydrogen here? If I have ethane, we have CH bond. So what is the bond length between carbon and hydrogen? It is 112 picometers. Can you tell me why there is a difference in the bond length between CH and CC? Why CC bond length is longer than CH bond length? So bond length, we mainly concentrate with respect to the size of the atoms. So carbon, these are both are carbon atoms here. So carbon and carbon are larger than hydrogen because hydrogen is smaller. So smaller the atoms, shorter is the bond length. So therefore, CH bond length is shorter and CC bond length is little bit longer over here in this alkanes. Now, the tetrahedral structure you can see here. This is how the tetrahedral structure looks like, wherein you can find the bond angle between, this is H if I take, this is C if I take, this is H if I take, the HCH bond angle is 109.5 degree, or to be specific, it is 109 degree 28 minutes. So this is the bond angle, HCH bond angle you can observe in case of alkanes. Any doubt you have in the structure of alkanes? Students, can you hear me? Are you concentrating?
Please unmute and answer, students. Please participate.
Any kind of confusions, doubts you have in this?
I am seeing your heads are shaking, but please unmute and say yes, no.
I can't see you. I have just closed the videos. Okay, anyways. I'll just assume that you are following. Is that so?
Students, can you answer quickly? Jerome, Evelyn, everybody tell me, Amok, Fuzail, say yes, you're following, not following. Please tell, sir.
Yes, sir.
Yes, sir.
Yes, no confusions?
No, sir. No, sir.
Okay. Yes. Now, see, in this alkanes, what kind of chains we can write? So we can write a straight chain alkane and we can write a branched chain alkane like this. So straight chain alkanes will be like this. We have CH3, CH2, CH3. So this is straight chain alkane. We call it as N-propane. Like this we can name it, N-propane. What about this? 1, 2, 3. The longest chain having 3 carbon atoms, we can call it as 2-methyl propane. This is the IUPAC nomenclature of this, 2-methyl propane. Now, this is branched chain alkane. So, alkanes can be a straight chain alkane, branched chain alkanes. Now, you must have come across alkyl groups. What is an alkyl group? Alkyl group means if I have CnH2n plus 2 as an alkane, if you remove an hydrogen from this, it becomes CnH2n plus 1. This is called alkyl. So when you remove one hydrogen from an alkane, it becomes alkyl. So when you remove one hydrogen from alkane, it becomes alkyl. Let me take this methane as an example and remove one hydrogen, it becomes CH3. This is methane and this is called as methyl, like this. Now, if I take C2H6, ethane, and when I remove an hydrogen here, it becomes C2H5. It is called ethyl. Like this, alkyl groups. Now, if I take CH3, CH2, CH3, this is propane, N-propane or propane it is. And if you remove an hydrogen, the question arises here. Here there is no problem. You can remove hydrogen from any carbon atom. But here, if you remove hydrogen from this carbon atom, so if I take a carbon atom here I'll just name number it as 1, 2, and 3 like this. Now, if you remove hydrogen from this carbon atom or this 1 or 3 carbon atom, both of these carbon atoms are equivalent. Terminal carbon atoms are equivalent. Equivalent in the sense, if you remove hydrogen from these, the type of alkyl group you will get is same. There is no difference in the type of alkyl group. We call it as N-propyl group. But when you remove hydrogen from the second carbon atom, you are not going to get the N-propyl group. So you are going to get the alkyl group something different. So here you will get two types of alkyl group. One is CH3, CH2, CH2. This is one type of alkyl group. And you can get another type is CH3, CH, CH3. So this is how you remove the second carbon atom hydrogen. Here you have removed the hydrogen atom from this. This is called N-propyl and this is called isopropyl. So there are two different types of alkyl group you will get like this. Similarly, for different types of alkanes, the alkyl group may be more than 1, 2, 3 like that, depending on how many different types of isomers of alkanes are possible. So I'll give you a simple assignment today. You just have to tell me in the next class, if I take a CH3, CH2, CH2, CH3, this is N-butane. It has one more isomer, that's what I have written here. This is called as isobutane. So this is, let me write 1 and this is 2. So these two are isomers. So these two isomers, what are the different types of alkyl groups? I can write total how many types of alkyl groups I can write. I want answer in the next class at least. Can you?
Yes, sir.
Yes.
Nora? Okay then. So let me continue with the next part of this. So in alkanes especially, we are classifying the type of carbon atoms into 4 different types. There are 4 different types of carbon atoms. One is primary, secondary, tertiary, and quaternary. So when we say primary, so primary carbon atom is the carbon atom which is attached with only one other carbon atom. So primary carbon atom. This is called primary carbon atom. Remaining all are hydrogens in this case. Remaining all 3 are hydrogens. Here remaining 3 may be different or hydrogen. If these are also hydrogens, then this also becomes primary. So carbon atom attached to only one other carbon atom is called as primary carbon atom. Now secondary carbon atom, what is secondary carbon atom? If I have like this. So this is secondary carbon atom if we have 2 hydrogens over here like this. So carbon atom attached to 2 other carbon atoms is called as secondary carbon atoms, and corresponding hydrogens are called secondary hydrogen atoms. Secondary carbon hydrogens attached to secondary carbon is called secondary hydrogens. We can also say hydrogens. Here these 3 are primary hydrogens. Now I hope you can now tell me what is tertiary carbon atom. Simply like this, if you have 4 bonds, I am satisfying with this carbon, all carbons, and if this is hydrogen here, and this carbon atom is tertiary. This carbon atom is tertiary carbon atom. So tertiary carbon atom means it is attached to 3 other carbon atoms. Simple way you can define it. Quaternary carbon atom, all the carbon atom attached to 4 other carbon atoms like this. No hydrogens attached here to this and this is called quaternary carbon atom. So we classify the carbon atoms in alkanes as primary, secondary, tertiary, and quaternary carbon atoms. So very important, you must understand this. It is very important to understand certain chemical reactions, their stability, everything. To understand that, you need to know what is the type of carbon atoms we have in the given compound. So we have primary, secondary, tertiary, and quaternary, 4 different types of carbon atoms in alkanes. This type of classification mainly we do in alkanes. Okay. So now I will take one example. Yes, now one by one you can answer. Let me number this quickly. If you can answer here, 1, 2, 3, 4, 5, and 6. Let me numbers randomly. I'm not taking any IUPAC nomenclature here. Simply I'm numbering it. So and let me take here 7, 8, and 9. So I have numbered all the carbon atoms over here. So can you tell me what is the first carbon atom, primary or secondary or tertiary? What is that type of carbon atom? First carbon atom.
Primary.
Primary. 7th carbon atom.
Primary.
Primary. 6th one. Primary. 8th one. Primary. 9th one. Primary. So all these are primary. What about second one?
Secondary.
Second one is secondary?
Tertiary.
Tertiary. Second one is tertiary because it is attached to 3 other carbon atoms and only 1 hydrogen atom, right? Now this is attached to 2 hydrogen. That also you can see. This is what? Secondary, correct? This is primary. This is tertiary. This is secondary. This is fourth one?
Quaternary.
Quaternary, absolutely right. This is secondary and this is primary. This is primary. This is primary. So like that, we can go ahead in identifying the type of carbon atoms in the hydrocarbons. Primary, secondary, tertiary, quaternary. So we have all four different types of carbon atoms I have taken in one example. So let me solve 1 or 2 examples on IUPAC nomenclature quickly because you have done it in detail in the first chapter. So now can you tell me longest carbon chain has here 6 carbon atoms, you can see. And these 2 are the substituents. Longest chain is hexane over here. And substituents you can take 1, 2, 3, 4 because the substituent must be getting a minimum number 1, 2, 3, 4. So alphabetically, this is called ethyl group. This is called methyl group. So alphabetically, ethyl comes first. Therefore, 3 ethyl, 2 methyl hexane. We can name it as IUPAC nomenclature. So this is one of the examples I have taken for how to solve with respect to IUPAC nomenclature. So let me take another example. Can you tell me where we number it from quickly? Left or right? Where the carbon atoms we number it from, which is the longest carbon? Longest chain having how many carbon atoms? Longest chain has how many carbon atoms?
5 carbon atoms.
Yes, 5. You have to number it from left side because there are 2 substituents to the same carbon atom which must get a minimum number. So 2, 2, 4 trimethyl pentane. That is what is the name of this. Yes. Now, another concept we have come across in this chapter is conformations of alkanes. So what do you mean by conformations of alkanes? Conformations means what? Conformations. Conformations are nothing but when it arises and why it arises. If we have carbon-carbon single bond like this, so conformations arise. So this bond, this single bond between the carbon atoms, is mainly due to the overlapping of sp3 hybridized orbital of one carbon and sp3 hybridized orbital of another carbon. And this 2 electrons here will be lying in the passing through the internuclear axis. Now, if I keep one of the carbon fixed and try to rotate this carbon atom like this, so what is observed? What we can observe is this carbon atom does not have any restriction. This bond is not going to get disturbed. Not much disturbance you can observe between the carbon-carbon bond because we are rotating along the axis itself. So therefore, the bond between carbon-carbon single bond does not get disturbed. So sigma bond is there. That sigma bond is not going to get disturbed if I rotate the other carbon atom, fixing the other one carbon atom. So as a result of this, what we observe, that is very important. So as a result of rotation around carbon-carbon double bond, say here we have, let us assume 3 hydrogens. Here we have 3 hydrogens. So the spatial arrangement between the hydrogen, see here this hydrogen and this hydrogen, this hydrogen and this hydrogen, tetrahedral geometry. There is a spatial, there is a, here this, the position of these hydrogen atoms are fixed, but position of these hydrogen atoms go on changing with respect to these hydrogen atoms. With respect to these hydrogen atoms attached to this carbon, which is fixed, which is not going to be rotated. This carbon, when I rotate, the CH bond, this spatial arrangement of this CH bond is going to vary with the spatial arrangement of this CH bond. That means there is a spatial difference in the relative spatial arrangements which arise because of rotation around carbon-carbon single bond. We call it as conformations. So we can rotate the carbon atom through 360-degree. We can maintain small angles, 0.1, 0.2, like that. We can maintain the small angles, n number of such conformations we can find. So such conformations of ethane we are going to learn over here. So this, let us take this one. See, in this particular example, I hope you are observing this 3-dimensional structure of ethane. Let us assume this is hydrogen, and this is also hydrogen. This also is hydrogen, hydrogen, and hydrogen. So now, if we have this CH bond and this CH bond like this, parallel, exactly parallel to each other, this CH bond is parallel to this CH bond, and this CH bond is parallel to this CH bond. So all CH bonds are parallel to each other exactly. So that means these CH bonds are nearest. These two are nearest to each other. These two are nearest. These two are nearest. So they are nearest to each other. So when that such all the 3 CH bonds are nearest to each other, we have one conformation that is called as eclipsed conformation. When all CH bonds with respect to each other, with this carbon and this carbon, with respect to this carbon carbon single bond, if CH bonds are nearest to each other, we call such conformation as eclipsed conformation. Now, carefully listen. When I rotate this, if I fix this carbon is fixed, and then if I start rotating this carbon, I'll start rotating like this. So if I rotate through very small angle between this CH bond and this CH bond, there is some angle is made, correct? So that angle between this CH bond and this CH bond is called as dihedral angle. So in this, when they are in their nearest possible approach, the dihedral angle is taken as 0 degree. So 0 degree is the dihedral angle when they have nearest approach. When I start rotating by fixing the other carbon atom, the position of the other carbon atom is fixed, whereas the one carbon atom position is fixed. And if I rotate the other carbon atoms through small angles, then dihedral angle goes on changing. So each dihedral angle will give one conformation for you. But our topic of concern here is mainly two conformations. So we can have infinite such conformations, no doubt in that. But we are going to discuss in this chapter mainly about two conformations. So one of the conformation is eclipsed conformation, as I told, when the CH bonds of adjacent carbon atoms are nearest to each other. See, this is these CH bonds and these CH bonds and these CH bonds. All the three CH bonds are nearest to each other, and therefore this is called as eclipsed conformation. Dihedral angle in eclipsed conformation is 0 degree. Whereas if I go on rotating through 0.1, 0.2, 1, 2, 3 degree with respect to here by fixing this, and if I rotate this, I go on getting 1 degree, 2 degree between this CH bond and this CH bond, the dihedral angle goes on increasing. So when I rotate through 60 degree, then CH bonds are maximum away from each other, maximum possible away from each other. So such conformation wherein CH bond of two carbon atoms are maximum away from each other are called as staggered conformation. So we can call it as staggered conformation when CH bonds of adjacent carbon atoms are maximum away from each other. So these are the two important conformation we need to understand over here. One is eclipsed conformation, another is staggered conformation. Remaining all are called as skew conformations. So two extremes we are learning here. One is maximum near to each other, CH bonds. Another is maximum away from each other, the CH bonds. So when you rotate through 60 degree angle, dihedral angle in case of staggered conformation is 60 degree. Dihedral angle in case of eclipsed conformation is 0 degree. So they at 0 degree means the CH bonds of adjacent carbon atoms are nearest to each other. In staggered conformation, the CH bonds are farthest away from each other. These are the two extreme cases we are learning here. Now, in these two extreme cases, how we can represent these two extreme cases? These two extreme cases are represented by two things. One is Newman projection and Sohor's projection. So in case of Newman and Sohor's projection, how we can write these two extreme cases? So in this projection, the molecules are viewed along the molecular axis and along a straight line. So we have to, on the paper, how we can represent these conformations, staggered and eclipsed conformations, how can we represent? So what we have to do here is, just observe here, we have to write a long line, tilted line like this. This particular point can be taken as rear carbon atom. This particular point is taken as front carbon atom, is towards the observer, it is away from the observer, behind. So you can say front and rear carbon atoms. Now to this front and rear carbon atoms, we have to represent the CH3 and CH3. This is CC, three bonds of hydrogens we have to represent for each carbon atom. So for say eclipsed and staggered conformation, how can we represent? So you can see like this. So here, this is how we can represent in case of eclipsed conformation. This kind of representation, you can see inverted Y over here. This is inverted Y, and here also we write inverted Y. Keep in mind that the angle between these lines, CH lines, will be around 120 degree here. Actually, it is not 120 degree, it is 109 degree, 28 minutes. But while representing Sohor's projection, we make it as 120 degree. So both are inverted Ys. So that means all CH bonds are nearest to each other. Now, to represent staggered conformation, I will fix this carbon atom and rotate this carbon atom through 60 degree. So if I rotate through 60 degree, I'll get something like this. So this is what is staggered conformation. So this particular one of this is kept as it is. You can observe here, this is kept as it is. This is not changed. What is changed here is this. So what we have done here, so we have just rotated this through how much degree? That is 60 degree, because you know dihedral angle is 60 degree. So staggered conformation, the dihedral angle is 60 degree. The representation would be like this. So very important to understand the eclipsed and staggered conformation. Now, can anyone tell me between eclipsed and staggered conformation, which is more stable conformation and why? Quickly. Which is more stable conformation?
Eclipsed is the most stable one.
Why eclipsed is more stable? What is the reason?
Not sure.
Not
But
sure.
because
Okay. Say for stability, very important, all of you listen here. For stability, what are the factors to be considered? There might be a lot of different factors to be considered as you go higher studies, but here mainly two factors we consider. One is torsional strain. You must understand what is torsional strain. And another is steric strain. There are two factors. So what is torsional strain and what is steric strain? So to be understood, I'll just explain that little later, because again, Newman projection also I have to explain you. So how to represent Newman projection for eclipsed and staggered conformation. So here, this is how we look this ethane. So this is one CH3 bond and this is behind, rear carbon atom also has CH3 bonds. So now this front carbon atom is just represented with a point like this. Front carbon atom which is towards the observer, and we write rear carbon atom with circle. Rear carbon atom with circle. And front carbon atom we write Y, inverted Y like this. Which is line, it has to pass through the circle only, outside the circle. So the CH bonds like this, CH3 for front carbon atoms, rear carbon atoms is represented by circle like this. And if I want to represent staggered conformation, you can see this part of the circle, you can just in the middle, you can write like this. This part of the circle in the middle like this. This is called staggered conformation, maximum away from each other. If I want to write the eclipsed conformation, I'll write just beside each hydrogen atom one more small lines, which is the CH bonds of rear carbon atoms. I'll just show you something like this. You can see the rear and front carbon atom represented. Dihedral angle for staggered is 60 degree. So you can see staggered conformation, which is represented like this. And you can just observe three-dimensional structure would be like this. Maximum away from each other, each CH bond. Now you can see eclipsed conformation. Just beside hydrogens, one more hydrogen, we write the red ones representing the rear carbon atom CH bond, the black ones representing the front carbon atom CH bonds. So this is eclipsed conformation, Newman projection, eclipsed conformation. So any doubt in representing the eclipsed and staggered conformation? Or understood what is the concept behind this? These are the two extreme cases I'm just discussing here, nearest and farthest. Remaining conformations, whatever angle you rotate, remaining conformations are all called as skew conformations or gauche conformations. They are called as skew or gauche conformations. Now, relative stabilities of conformations. That's what I wanted to discuss. Now, staggered conformation is the most stable conformation, not eclipsed. That you must keep in mind, very much important. Eclipsed is least stable one, whereas the skew conformations are in intermediate between staggered and eclipsed. It is less stable than staggered and more stable than eclipsed conformation. So that is relative stability. So the eclipsed conformation, what is the important criteria is bonds are very near, as I told, farthest CH bonds are nearest to each other. Whereas in staggered conformation, bonds are maximum distance, have minimum repulsive interaction. Say if I take CH bonds between the carbon atoms, CH bonds between the carbon atoms, this is very nearest to each other. That means this bond pair of electrons are nearest to each other and there will be a repulsive interaction between these bonded pair of electrons. So therefore, when the bonds are very near, there will be a repulsive interaction, more repulsive interaction. In staggered conformation, the CH bonds are maximum away from each other. Therefore, minimum repulsive interaction between the bonded pairs of electrons. Because electrons are same charges, they must repel with each other. So there will be a minimum repulsion in staggered case, whereas maximum repulsion in case of eclipsed conformation. So that you must remember and understand here very clearly. Any doubt here? So we call that as torsional strain. So torsional strain is repulsion between the bonded electrons of two different bonds leads to torsional strain. So carbon-carbon sigma bond rotation is hindered by small energy barrier about 1 to 20 kilojoule per mole. So weak repulsive interaction between the adjacent bonds. Because rotation is free, I said, but not completely free. It will have some energy barrier. You need some energy to rotate. So we can get that energy by the room temperature itself, no doubt in that, but there is some energy barrier is required for the rotation. So there is a repulsive interaction between the bonded pairs of electrons. We call it as torsional strain. So magnitude of the torsional strain depends on the angle of rotation about carbon-carbon bond. So the magnitude of torsional strain is maximum in case of eclipsed conformation. The magnitude of torsional strain is minimum in case of staggered conformation. Any doubt in this? What is meant by torsional strain? Everyone understood this? Repulsive interaction between bonded pairs of electrons. The torsional strain is highest in case of eclipsed, as I told, and it is minimum in case of this one. One more type I told, one more factor which is affecting the stability of conformation is steric strain. In case of ethane, as an example, steric strain is minimum. You can ignore steric strain over here. Steric means size, based on this size. Now, in ethane, we have taken all hydrogens here, right? So hydrogen atoms are very small. So since they are very small, there is no steric hindrance will appear between these two hydrogen atoms. Now, instead of hydrogen, if I have, let us say, CH3 here and CH3 here. Instead of hydrogen, we have some bulkier groups attached. Then the steric strain comes into picture. When the size of the group or atom attached to the carbon-carbon single bond, the size of the atoms or groups attached to the carbon-carbon single bond is a larger size, then along with the torsional strain, steric strain also to be considered for stability. So for stability, steric strain is also considered when the size of the atoms or groups attached to the carbon-carbon single bond, if it is larger. So then only steric strain will come into picture for understanding the stability. So if two atoms or group of atoms brought together, an attractive force developed between unequal distribution of electrons. Similarly, if the size is there, repulsive interaction also may possible between them. So if the size is very large, there will be a large repulsive interaction between the groups or atoms. So therefore, that will cause the steric strain among them, and the stability of that molecule is going to decrease. So if the group, say this particular group attached here, CH3, here also it is CH3. So if they are attached bulkier groups, they come very near to each other. And when the groups come near to each other, there is no much space for them here to accommodate. So therefore, if there is no much space for them to accommodate, there will be a repulsive interaction between them. So that is causing the instability in that particular compound. Say I have taken this for you. Quickly, I can go through this here. This is an eclipsed conform. This is energy axis, you can observe. This is an energy axis. This is an eclipsed conformation wherein dihedral angle is 0 degree. Correct? So dihedral angle is 0 degree. Now, if I rotate this CH bond through some angle, so its energy goes on decreasing because the torsional strain decreases, because here eclipse conformation, CH bond are nearest to each other. So they start going away from each other. The torsional strain goes on decreasing, stability goes on increasing. When I rotate through 60-degree angle, it reaches the staggered conformation. Again, further, you can observe with respect to red here. So red means CH bond E with each other will be maximum. Then again you rotate through 60 more degree, again it will come back to the original eclipsed form. Again, if you rotate through 180 degree, again it will be staggered one. Again rotating through 240 degree, eclipsed, staggered. It is for ethane case. This is for ethane case. So you can have staggered conformation when you rotate through 60 degree, 180 degree, 300 degree. You will have eclipsed conformation when it is rotated through 0 degree is one, and when it is 120 degree, 240 degree, and also 360 degree. So this is how you can say stability, lower the energy, more is the stability. So staggered conformation has the lowest energy over here. Therefore, maximum stability you can observe for staggered conformations. Yes. Now coming to one more example I have taken for explaining the steric strain. Quickly, I can go through this. So this is the eclipsed conformation. Eclipsed conformation wherein CH3 are nearest to each other. HH are nearest to each other. CH are nearest to each other. So all the three are nearest to each other. This is eclipsed conformation. When I rotate through 60 degree, this is the angle between this is 60 degree. So the CH3 are not farthest here. They are not farthest. They are somehow away from each other. The steric strain is less and also torsional strain is less. Energy is decreased up to this. Further, if I rotate, the CH3 will come here in this case, will come here. There is again, the bonds are nearest to each other. Torsional strain is more. Their steric strain is less, but torsional strain is more. Energy is going to increase. Further decrease, if I go on rotating like this with respect to CH3, I can see here CH3, you will have maximum apart from each other. So this is the maximum stability conformation. This is called staggered conformation when you rotate through 180 degree. This is the case of butane. As I already told you in the last part of this. So butane, you will have staggered conformation. So again, here you will have some other conformation which is having similar to this energy. This is the, again, come back to the original state. This is what is called as eclipsed conformation. So rotation through different angles. Here steric strain also to be considered for understanding the stabilities of the conformations. Any doubt you have in that conformations? It's important for CET also. Any doubt?
No, sir.
Okay. Understood
sir.
the concept over there? Okay. So now let us briefly discuss about the preparation of alkenes. So mainly we have three types of preparation methods in the NCERT text. One is from unsaturated hydrocarbons, another is from alkyl halides, another is from salts of carboxylic acid. So we can just go through for these unsaturated hydrocarbons. So we can take unsaturated means alkenes or alkynes. So alkynes and alkenes, if I take carbon-carbon double bond like this, carbon-carbon triple bond like this. So how I can prepare the alkanes from this is, I have to convert this double bond into single bond. I have to convert this triple bond into single bond. And I can add only hydrogen because it is hydrocarbon. I have to add only hydrogen here, nothing else, no other element, only hydrogen to be added. So if I want to add hydrogen, I have to use hydrogen only, H2. Hydrogen gas only I have to use. And I have to add hydrogen gas to both of these so that I can prepare this alkane. So here, if I add one hydrogen here and one hydrogen here and make a bond, now carbon has 5 bonds. So 5 bonds it can't have. Therefore, one of the double bond becomes single bond. Like that, remaining all must either carbon or hydrogens, like that we will have. So addition of hydrogen, we can call the reaction as hydrogenation reaction. So hydrogenation reaction can happen in the presence of nickel, platinum or palladium. If you use nickel, you will have to maintain little bit higher temperature because it will get activated at higher temperature. Palladium and platinum, lower temperature only you can use as the catalyst over here for hydrogenation reaction. So it is hydrogenation of alkenes and alkynes, you can say, for preparing the hydrocarbons. So you can see alkene CnH2n is the general formula of alkene. Nickel, when you, in the presence of nickel, when you add hydrogen, CnH2n plus 2 hydrogens are added over here. This is one of the examples you can take. So hydrogen, single bond hydrogen, one carbon, another carbon, you can add 2 hydrogens over here, and single double bond becomes single bond, because carbon can have maximum 4 bonds only. So therefore, you can just go through these examples. It is one of the methods of preparation of ethane and propane. Addition of 1 mole of hydrogen to alkenes, where the hydrogen gets added to carbon-carbon double bond, and double bond becomes single bond during this. So this is called the hydrogenation process. You can either use nickel or platinum or palladium as a catalyst during this hydrogenation process. So this is one of the methods of preparation of alkanes, sorry. Now, similarly for alkynes. Now, I'll ask you a question here. For alkenes, we have used 1 mole of hydrogen to get alkane. So here, how many moles of hydrogen I need for converting this alkyne into alkane? How many? Simple. So when I add one hydrogen here, triple bond becomes double bond. I want single bond between the carbon atoms, means one more bond has to be replaced with one more hydrogen, right? So we overall should have 2 moles of hydrogen. So that's why we need here 2 moles of hydrogen for preparing alkanes from alkynes. So 2 moles of hydrogen. Triple bond has to be converted into single bond. So triple bond has to be converted into single bond. So 2 moles of hydrogen are required for converting alkynes into alkenes. Any doubt? Yes. Next one is another method from alkyl halides. So by the reduction process. So we call it as reduction. So why we call it as reduction? Because you know, reduction process is removal of an electronegative element or addition of an electropositive element, or addition of hydrogen, you can say. So here X is an electronegative element. If this is removed by somehow, by adding this electropositive element to this, we can call it as reduction. That's why alkyl halides, when they undergo reduction, except fluorides, because CF bond is very strong, by this method it has been very difficult to break the CF bond. So it is very easy to break other bonds like CCl, CBr or Ci bonds. It is easier, whereas CF bond breaking is very difficult. So zinc in presence of H plus, you know, zinc is highly reactive, and zinc releases hydrogen gas or nascent hydrogen when added with dilute acid, dilute HCl or dilute H2SO4. So when you add zinc to this, it releases hydrogen gas. So that hydrogen is used for this reduction process. So in this reduction process, to remove this CX bond, to break this CX bond and add this CH bond, which is more stronger bond. So we get this reduction process is done by adding zinc into dilute acid. So this is how we can perform this reduction process. Zinc in dilute acid releases nascent hydrogen. That nascent hydrogen replaces X in the alkyl halide. So it is meant by alkyl halide. Alkyl halide means the alkanes, in alkanes, one of the hydrogen is replaced by halogen. That is called as alkyl. You know alkyl group, right? One hydrogen less than alkanes is called as alkyl. So that one hydrogen is replaced by this halogen. So therefore, we call it as alkyl halide. So that is what we have. So this is CH3Cl plus H. Like that, one example I have, zinc and H plus. We can take methane as the product over here. because one of the hydrogens added over here is this. Now, another example I have, the product what we are getting here is ethane. So ethyl chloride, zinc H plus, we can get ethane as an example. Chloroethane, we get ethane. So apart from zinc HCl, we can also use other reducing agents like zinc acetic acid, zinc NaOH, zinc copper couple with ethanol. All these release hydrogen. HI red phosphorus. All these are going to release hydrogen for the reduction process. That's why we can use other reducing agents also in this case for this reduction of alkyl halides to alkenes. Any doubt in this? Another important reaction is Wood's reaction. So Wood's reaction is nothing but the conversion of alkyl halide into alkanes by reacting with sodium in dry ether. Very, very important to understand. I'll just show you the general reaction. See, if you use the same alkyl halide here, 2 moles of alkyl halide, 1 mole here and 1 mole here. These 2 moles of alkyl halide, this is Rx, this is also Rx. So you can remove this NaX here. And the important point to be remembered here is we have to use dry ether. So the reaction has to be carried out in the presence of dry condition and non-polar solvent like ether. So ether is an organic solvent which is non-polar solvent. And dry in the sense it must be free from moisture. Say if you have moisture present, so that moisture contains water and water can react with sodium and forming sodium hydroxide. So sodium is not at all available for this process. That is one thing. Another possibility is Rx can also react with water and gets converted into ROH, alcohol. So this is another possible reaction with this. And hence, very important point to be remembered here is in this reaction, Wood's reaction, we have to use dry ether for the reaction. So that this R and this R gets connected with each other. You can observe here the 2 R's are connected with each other. So 2 alkyl groups connecting with each other will get alkane only. Say, let us say CH3, CH3 means C2H6, right? So this is C2H6. This is one methyl group. This is another methyl. So we can get C2H6 higher alkanes we can get as a product here. So one important point to be noted here in this Wood's reaction is if you are using an alkyl halide for the Wood reaction, always you will get the alkane with even number of carbon atoms. Only even number of carbon atoms only we can get. So if I use one of the types of alkyl halides, only even number of carbon atoms. That means you can't prepare methane from this method. Very important point to be noted. Methane cannot be prepared by Wood's reaction. Methane, because methane has one carbon atom, odd number of carbon atoms. Therefore, this method, Wood's reaction, you can't prepare methane. And one more question arises over here. Can't we prepare alkane with odd number of carbon atoms? Yes, it is possible to prepare alkane with odd number of carbon atoms. So what is the method of preparing that, and why is it feasible, or is it giving you enough yield for the particular reaction? That also is to be understood. Now, coming to one more point here before I go to that mixed odd number of carbon atoms. So here, order of reactivity for alkyl halides. R is an alkyl group. R is nothing but Cn, H2n plus 1. One less hydrogen in an alkane. That is called alkyl group. So R, if it is attached to iodine, bromine, chlorine, fluorine, which is the fastest reaction it can undergo, order of reactivity. So which Rx bond can be broken very easily? Rx means halogen. So halogen can be FCl, Br or I. So which bond is weakest over here is Ri bond is weakest. Can anybody tell me Ri bond, why is it weakest compared to RBr, RCl and RF?
The electronegativity, sir.
No electronegativity, not Here, bond strength is talked with respect to size and bond length. So if I take F, Cl, Br, I, smallest size is F, biggest size is I. Size increases down the group in 17th group elements, right? So size increases means the bond length increases. The length between R and I bond is longest. So bond length is long means that bond can easily be broken. So based on size of the halogen atom, larger the size of the halogen atom, longer is the bond length between carbon and halogen, and easier is the way we can break that bond. So therefore, Wood's reaction can easily be carried out if you have Ri, iodides. Iodides are very reactive, followed by RBr, followed by RCl, followed by R. Last one, least reactive is RF. This is the point to be understood. Now, I'll take the Wood's reaction when different alkyl halides are taken in the mixture. Let us take, this is ethyl bromide. This is methyl bromide. Now, in the mixture, I have taken mixture of two alkyl halides. One is ethyl bromide, another is methyl bromide. So, mixture of two alkyl halides when I take, see, if I can do, is this the only possibility? Can anyone tell me? Sodium bromide is lost over here, no doubt in that. And you can get propane here, right? Or odd number of carbon atoms. This has two carbon atoms, this has one carbon atom. But this is not the only possibility over here in Wood's reaction. There are other possibilities also there, because there are lot of ethyl bromide molecules are there in the reaction mixture. Lot of methyl bromide molecules are also there in the reaction mixture. So this is one of the possibilities, no doubt. But if there are two C2H5Br, another C2H5Br molecule, if these two react with sodium in dry ether, then this is the loss, and C2H5 will connect with each other. How many total number of carbon atoms now? 4. 2 plus 2, 4. Butane you will get. Similarly, CH3Br and CH3Br you can take. These two also can react with sodium in dry ether, right? BrCH3. So you can just remove this sodium bromide. CH3 will get connected. Ethane you will get C2H6. So there are three different possible products you can get here: propane, butane, and ethane. It is a mixture of three products, and all these three are have very less difference in their boiling point. Separation becomes very, very difficult. So separation of these alkanes become very difficult. No doubt we have prepared a alkane containing odd number of carbon atoms, but we have not prepared alone. We have prepared it along with some other alkanes also. Therefore, it is not advisable to use this method for the preparation of alkanes containing odd number of carbon atoms, and it is advisable for preparing the alkanes of even number of carbon atoms. If you want an even number of carbon atoms, alkane containing even number of carbon atoms, then you can use this method of preparation of alkanes. That is one of the drawback of this Wood's reaction. You can't prepare the alkane with odd number of carbon atoms. Here, one more point I have added. In case of dihaloalkanes, intramolecular Wood's reaction takes place. So what do you mean by this intramolecular Wood's reaction? I'll just take one example here. Cl, CH2, 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 Cl. Now, if I have a dihaloalkane, it is 1, 2, 3, and 4. 1, 4 dichlorobutane it is. If I do reaction with sodium in dry ether, what is the product we can get here? So we can get the product. This sodium removes this Cl also, this Cl also. Wherever you are removing the Cls, connect those two carbon atoms. You connect this 1 and 4 carbon atom and make a cyclic compound like this, CH2, 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 CH2 like this. We call this as cyclobutane, which can be represented simply like this, cyclobutane. So Woods reaction, you can say this is called as intramolecular Woods reaction. Within the same molecules, two Cl atoms are removed by sodium here, making a cyclic compound. So you can get cycloalkanes as the products over here. Cycloalkanes as the products. Understood this? Any doubt?
No, sir.
Yes. So last one more method is you can prepare from carboxylic acids. What are carboxylic acids? So salts of carboxylic acid. RCOOH is carboxylic acid. All of you know this. Carboxylic acid. What do you mean by salts? So when this carboxylic acid is treated with a base like NaOH, you are going to get RCOONA, RCOONA, RCO minus Na plus water. This is called sodium salt of carboxylic acids. So from such sodium or potassium salt, if I take KOH here, you're going to get potassium salt. So sodium or potassium salts of carboxylic acids, we can prepare this hydrocarbon, that is alkane. So there are two methods. One is called as decarboxylation of sodium salt of fatty acids. Decarboxylation of sodium salt of fatty acid. Decarboxylation means removal of this carboxylic acid group. D means removal. Carboxylation means carboxylic acid group. This entire group is being removed during this process. So for this decarboxylation, what we are using here, the reagent is mixture of NaOH and CaO. So we are going to use mixture of NaOH and CaO for this. So now NaOH and CaO is called as soda lime. It is known as soda lime. And it is a decarboxylating agent. Remember this, very, very important reagent. NaOH plus CaO, decarboxylating agent. So now you can see the reaction here, general reaction I'll give you. Now you can observe here what is happening. NaOH is reacting and it is being removed as Na2CO3. You can observe in this bracket what we have written here. Na2CO3, it is been lost. And this hydrogen is attached to this alkyl group, and alkyl group with one hydrogen is nothing but alkane. So alkane, then you can say, we can ask what is the role of the CaO? So CaO has an important role to play here is NaOH is called hygroscopic. It has very much affinity for water, hygroscopic. It has very much affinity for water. CaO's role is to keep this NaOH dry. It has to keep NaOH dry throughout the reaction. Because whenever moisture comes into picture, so CaO will absorb that. CaO, calcium oxide, will absorb that and keep this NaOH dry throughout the reaction. So throughout the reaction, you need to keep this NaOH dry completely so that it can act as decarboxylating agent. So CaO actually keeping the NaOH completely dry throughout the reaction. So alkane you are going to get. And you can observe one more point in this reaction. This is the R is carbon chain. This is the carbon chain you have. So this carbon chain may have 1, 2, 3, 4, 5 carbon atoms. No doubt in that. The number of carbon atoms may be different. Plus 1 carbon atom in the carboxylate group. This is called as carboxylate group. COONA. COO minus group is called as carboxylate group. So this carboxylate group has 1 carbon atom. Means total number of carbon atoms in this sodium salt of carboxylic acid is R plus 1. So after the formation of alkane, you can observe this carbon is been removed. That means the number of carbon atoms is 1 less than the carboxylic acid. So you are getting the product, what you are getting, the number of carbon atoms in the product, 1 carbon atom less than the number of carbon atoms in R, in carboxylic acids. So one less carbon atom, R plus one carbon atom, and here we have R carbon atoms. That's all. So the question may be asked based on this in CET. So what is the product obtained? There might be different reactions may be given. Let me take one example here like this. You can observe in this example, see, it has two carbon atoms and it has only one carbon atom, methane. So you can say, observe here, methane can be prepared from this method. Methane can be prepared from this method. So this method, you can see there are three carbon atoms in the carboxylic acid, whereas in the product, you have only two carbon atoms, which is ethane. So one less carbon atoms in the alkane you can obtain when decarboxylation is done with the soda lime. The soda lime composition is NaOH-CaO. That you must remember. It will help you in second year also. This reaction will help you in second year also. Very, very important reaction it is. One more is coal-based electrolysis. This is also from carboxylic acid, sodium salt of carboxylic acid. Everything is same, but the method is different. So method is electrolysis. What do you mean by electrolysis? I hope everyone knows. Electrolysis is nothing but passing electric current through the electrolyte solution. So electrolyte solution is the one which conducts electricity when you pass electric current. So sodium salt of carboxylic acids are electrolytes. So when you pass aqueous solution through those aqueous solutions, when you pass electric current, what happens? That's what we are going to learn here. This is the general reaction. So you can observe sodium acetate. You have, this is called as sodium acetate or sodium ethanoate is the IUPAC name for this. When you electrolyze this, you are going to get ethane as a product. Ethane as the product. And byproducts are carbon dioxide, hydrogen, and NaOH. That means this part will convert as carbon dioxide. And Na plus, and in water we have H plus and OH minus. So Na plus will combine with this. And this 2H plus will get converted into, so to hydrogen, it will be releasing hydrogen gas over here. So this water is going to release now hydrogen gas over here. So this is going to be like this. The products, what are the byproducts obtained in this reaction? So if I explain you the mechanism behind this is very important. So in this, what happens in the cathode, what happens in the anode, I'm just going to explain you. Just carefully listen over here. Now, coming to this is the aqueous solution. When I add water, it is going to dissociate as acetate ion and sodium ion. Now, acetate ion will have 1, 2, 3, 4, 5, 6 electrons around this. Octet of oxygen is completed. That's why one extra minus charge is there on this. Now, one acetate ion loses one electron because anode is positively charged, cathode is negatively charged. So anode attracts anions because it is positively charged, attracts negative charges. So when this acetate ion reaches the anode, what will happen? Anode will try to take electrons from this. So one acetate ion gives one electron. So that means out of 6 electrons on oxygen, 1 electron is given to anode. Likewise, we have 2 acetate ions. Each acetate ion has given one electron. Total number of electrons is 2. Therefore, around oxygen atoms, now we have only 5 electrons. It is a free radical called as acetate free radical. Now, what happens in the next step is, this part will undergo homolytic cleavage. You know, I hope you know homolytic cleavage means what? There is a 2 electrons here, 1 electron shifts to here, 1 electron shifts to here in this free radical, so that it will get a stable methyl free radical. So here, this carbon will get 1 electron unpaired. Here we have 1 unpaired electron, and these two will share and form carbon dioxide, because carbon dioxide means C double bond O, like this. So this is carbon dioxide, and methyl free radical is formed. And this 2 methyls there are so many number of cross togethers of methyl free radicals are formed, out of which 2 methyl free radicals are going to combine with each other and form. That means this is an unpaired electron. This is an unpaired electron. They share. That's all. There is a bond between these two carbon atoms. That's why we are going to get ethane over here. So what you have observed in this? So again, we are getting even number of carbon atoms. Alkanes with even number of carbon atoms. In this also, we can't prepare methane one. So methane can't be prepared from this method. One more point to be noted. All of you understood this mechanism? Any doubt? Understood this mechanism?
Yes, sir.
Any doubt you can ask. So this is the mechanism behind this. No need this actually. This is not required for you. This is not required for you. Leave it. Now, coming to how to identify the number of carbon atoms. As I told, in case of decarboxylation, the alkanes will have number of carbon atoms in the carboxylic acid -1. In coal-based electrolysis, what is the total number of carbon atoms in the alkane is equal to 2 into number of carbon atoms in the carboxylic acid. Say if I take CH3, CH2, C double bond O minus Na plus. If I take this, what is the product I'm going to get? Let me take here. So here there are 3 carbon atoms. I'll make it 2 into 2, 6, right? So 2 into number of carbon atoms in the carboxylic acid. -2, that means 4. So 4 means it is butane. The product obtained here is CH3, CH2, CH2, CH3. Even number of carbon atoms. Butane is obtained if I electrolyze sodium propionate, we call it as. So likewise, we can identify what is the total number of carbon atoms which we can obtain from coal-based electrolysis in the alkane. Even number. So here you can also even number. Butane can be obtained from this electrolysis of sodium propionate. So this is how we can understand the preparation of alkanes. Any doubt in this?
Oh, sir.
Additional information, you don't need this right now, leave it. This is not NCERT. Next year, we're going to learn all these things anyway. But in this chapter, you don't have all these. I'll just remove these slides later. Now, physical properties when you come across. Alkanes are non-polar because of covalent nature of carbon-carbon bond and carbon-hydrogen bond. They are non-polar because the electronegativity difference between these two carbons and carbon and hydrogen is very, very less. And because of that, they are completely non-polar, we say. When we say polar, when there is an electronegativity difference between the covalently bonded atoms, but there is no much electronegativity difference we can observe. Therefore, these are non-polar. So between the molecules, say if here we have one ethane molecule, there is another adjacent ethane molecule is there, C2H6 and C2H6. What type of interactions we can observe here is very weak van der Waals force of attraction. We call it as London forces of attraction, or we can call it as dispersion force. So dispersion force or London force of attraction. Weak van der Waals force of attraction between the molecules of alkanes. As molecular weight increases, force of attraction also increases. Say, as we move from lower member to higher member, molecular mass is going to increase anyway. So when the molecular mass is going to increase, so you are going to get the more attractive size of the molecule goes on increasing. So when size increases, attractive interaction between the molecule also increases. So that is surface area of the molecule increases means you can get the more attractive interactions between the molecules. Now coming to state, the alkanes 1 to 4 carbon atoms are gases, whereas 5 to 17, if you take, they are liquids, and above 17 carbon atoms, if you have any hydrocarbon alkanes, they are solids. They are volatile solids, you can say. They can easily be vaporized. So if you look into the boiling point, so boiling point, to analyze boiling point, 3 points are required. One is molecular mass. Higher the molecular mass, more is the boiling point. Very simple. Another is size. Larger the size, more is the boiling point. Because larger the size, more is the attraction between the molecules, more is the boiling point. Another is intermolecular interaction. Intermolecular interaction. So in this alkanes, intermolecular interactions are not much because they are very weak Van der Waals force of attraction is there. So therefore, we mainly consider these size and molecular mass. So as the molecular mass increases, size increases also, and also boiling point increases. But if we have two compounds with the same molecular mass, how to identify which is having more boiling point, which is having less boiling point? Let me take one example here: CH3, CH2, CH2, CH3. This is N-butane. CH3, CH, CH3, CH3. This is isobutane. Among these two, which one will have more boiling point? This is straight chain alkane. This is branched chain alkane. So straight chain alkanes will have more boiling point than branched chain alkanes, because straight chain alkane size is more, branched chain alkanes surface area is less, size is less, therefore boiling point. Both are having same molecular mass here, but size varies because of branching. So as the branching increases, boiling point decreases. Very simple way you can understand. Branching increases, boiling point increases. Sorry, decreases, not increases. Boiling point decreases. So example, you can say N-pentane means like this: CH3, CH2, 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 CH3. This is N-pentane. Isopentane means CH3, CH, CH3, CH2, CH3. This is isopentane. Neopentane means like this: CH3, 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 CH3. This is neopentane. All are having same molecular mass, but branching is increasing from N-pentane to isopentane to neopentane. So therefore, boiling point decreases as the branching increases. All are having same molecular mass. So molecular mass doesn't have any effect on this. Only size or surface area is going to decide the boiling point of this. Yes, this is what we have in physical properties. I hope we can conclude the today's class, and we can continue with chemical properties and alkenes and aromatic hydrocarbons in the next class. Is there any other confusion, doubt you have in whatever is dealt in the today's class? Please let me. Excuse me, sir. Are you there, sir?
Yes, sir. Yes, sir. Sure, sir. Students, I hope.
Shall I conclude, sir, today?
Yes, sir. Yes, sir. We can conclude it here today, and we can continue in the next class. Sir,
next sessions. Yes, absolutely.
Yes, sir. Students, whatever sir has covered today, I think very clearly sir has explained. I want you to go through all these points. I think you have made some notes on the notebook. Also, read your textbook, and any doubts that you have in the next class.
Better you come prepared for tomorrow's class. So tomorrow's class, if you come prepared, that would be very much helpful in understanding this also. So whatever confusions you have, you can clarify your doubts tomorrow. No issues with that.
Thank you very much, sir.
Yes, sir. Shall I stop sharing, sir?
Sure, sir. Sure, sir.